Okay, great. Okay, so I will start now then with a brief introduction. So yeah, hello everyone. It's great to be here, sharing some knowledge about some of the work that we've been doing. So yeah, I'm Sukrit Sakya. I'm currently working as CTO at Teras Technology. We are based in Kathmandu, Nepal. So basically, we are a healthcare software company, and we've been working uh, on building various AI-enabled healthcare applications, focusing the most part in medical imaging applications. And yeah, as uh, yeah, as you might also know, we've been working closely the different teams at the we are working on collecting. We are working with all the teams, providing them with the software solutions necessary to collect the ultrasound scans and collect other various patient-related data as well. So yeah, that's what I've been. That's what I do at Terras Technology, and that's what we do at our company here. So yeah, so I'm just gonna go through the outline of my short presentation here, some knowledge and some experience of I'll be going through the ultrasound data collection process itself and the various technical infrastructure required for ultrasound data collection and how it looks like and how the data collection pipeline looks like how the ultrasound data comes in along with other various patient data and goes to a central store and how it can be accessed for further use for the clinical uses or even the or specifically the annotation use case that we are focusing on right now. And I'll also share some uh, we've faced so far. Annotation process, like how we are facilitating the annotation process for various stakeholders to annotate the ultrasound data to to create high quality data sets for model training. And yeah, I'll also be going through a few examples of our work. And yeah, so that's going to be the outline of my presentation. So yeah, to get started, uh, let's talk about ultrasound data itself. So I think you might already know that ultrasound scans are basically DICOM files. So DICOM stands for Digital Imaging and Communications in Medicine. So it is the standard format used in healthcare imaging, specifically medical imaging, for storing, transmitting, and sharing medical images and other patient-related metadata. So yeah, DICOM files can be ultrasound scans, they can be X-rays, CT scans, MRIs, and so on and so forth. And so technically speaking, each DICOM file has two parts in it. So one is the metadata, and one is the image data itself, which is the actual pixel data or the actual medical image. So it can be, like I said, the CT, MRI, X-rays, and so on. And along with that, one specialty of DICOM files is that it can also store other relevant information in the form of metadata. So have this metadata embedded in those files as well. So the metadata can be information about the study and parameters and whole lots of other information as well. So these come embedded from the medical imaging modality devices itself.
We are losing you a bit. You're breaking up a bit. I'm not sure. Maybe you can switch off your camera for now and see whether that fixes it a bit. Yeah.
Okay, sure.
Yeah.
Okay, so is it better now?
Yeah, we can hear you. You might want to go back to the slides. We can't see the slides yet.
Okay, so is it visible now?
We can see your screen, but we are seeing the Zoom meeting screen. Yes, now the slides are visible.
Okay. Okay, yeah. So I was talking about the metadata in the DICOM files. So were you able to hear me? Or should I repeat that part again?
You can repeat that part because it just broke off a bit.
Okay, sure. So yeah, I was just saying that one specialty of these DICOM files is that they have the metadata. They can actually have the metadata embedded in them itself. So, for example, the data that was entered in the ultrasound machines or the CT machines, they are embedded in the DICOM file itself, so which allows us to basically grab essential information from the metadata itself without having to grab them or get them from any other external sources. So yeah, that's some specialties of DICOM files. So yeah, basically ultrasound is DICOM, in data that we have in medicine. So basically all medical images are DICOM. Yeah, so that's a brief introduction about ultrasound data. So from there, I'd like to move on to how or what kind of approaches can be taken to get the data from the ultrasound imaging modalities and store them in a central store, because that part is really important. So in basically most of the clinical scenarios, at least in our country, Nepal, and it may be true in most of the countries in the global south as well. So the use of a PACS or a central store. So PACS stands for basically Picture Archive and Communication System. So basically, it is a system that allows us to store these medical images in a central server. And these systems can talk in the language that these DICOM files understand. So technically speaking, DICOM files have their own protocol as well, in which they can communicate between each other. So the different imaging modalities, such as the ones in my slide here, so it can be a on-site ultrasound machine, or it can be one of these handheld devices, for example. So these machines can communicate with a PACS server in the DICOM protocol. So what that basically allows is for us to send these medical images, or in our case, these ultrasound clips from these sources, which can be these on-site ultrasound machines or these handheld ultrasound devices, and get the data from there and send them to a central store, which is called the PACS. So this part is very essential in data collection uh, or in clinical use cases as well, because uh, it's quite essential to store these use for archiving, or in our case, PACS is a very important part in the infrastructure which allows us to store these ultrasound scans for further use cases. One of them being annotations, of course. So this is how it would look like in the form of a diagram. So we can have various data collection sites, like for example, I'll try to come up with a simple scenario. Like let's say there are 3 hospitals, and we've decided to, let's say, collect data from those 3 hospitals for the study. What the data collection pipeline would look like the data collection setup would look like is that pieces can be connected to a central on site by the clinicians, by the radiologists. They can select the studies, the scans that they want to send to the PACS, and those scans can be sent over to a central PACS where they will be stored centrally. And yeah, as I said, after they have been stored here, this data can be used for various purposes. So of course, the clinical purpose is one of the use cases. And also, yeah, for dataset creation, for AI model training, they can be used for further annotations and labeling. But one thing which is quite important here is that for clinical use case, the data might not be anonymized because it's the clinical use case, and the clinicians need to know about the patient while accessing that data. But during the annotation process or using the data for any kind of model training, it's standard practice to anonymize the data. So basically, what anonymization means is that, as I mentioned in the previous slide, these DICOM files might contain patient information in the form of metadata. So it might contain the patient name, for example, the age, the gender, and other relevant patient information. So during our annotation process, we have to make sure, or we've been making sure that the patient data is anonymized before it gets to the annotators. So that's a very critical step, because we don't want patients' personal information to be exposed to the annotators. Yeah. So this is how the overall setup would look like. So basically, so this is not the whole setup actually. So this is a very minimal diagram that I have put here. But this is the essential part basically. So we have data coming into a central PACS, and from there the data is anonymized data is grabbed and used for further uses. So to say that in words, so basically this is how it would look like again. So the data or the ultrasound scans is collected on site by the clinicians and sent over to the central PACS. And other relevant patient information can also be recorded. So, for instance, in our projects, we've also been recording some relevant patient information uh, in our which we need in our use case, like the demographics of the patient and the clinical history and so on and so forth. So yeah, so on site, these data are collected along with the scans. And yeah, I mean, as mentioned in the previous slide, these anonymized studies are stored in a central location, in a central PACS. And yeah, as you might also know that ultrasound studies can contain clips. So technical terminology for these clips is they are basically multi-frame DICOM files. So the clip that we are able to play, that basically is that consists of basically multiple frames. So those clips are called multi-frame DICOM files, and also there can be some relevant static files as well. So by static files, these are basically single frame DICOM files. So these are not playable. So they can be, for instance, reports that were generated on site on those ultrasound machines, or they could be some frames with some annotations itself that were done on the ultrasound machine itself with some measurements or with some calculations as well. So here on the left, so this is just a screenshot. It's not playable actually. So this is a multi-frame DICOM file. This is a clip basically which can be played through. So it contains multiple frames. And this, for instance, is a static file, and this also is a static file. So here on the left, in the middle, sorry. So this is an example of a static file that was generated on the device itself by the clinician with some annotations. Here, as you can see, there's a landmark being drawn here, and here we can also see various calculations embedded in the image itself. And here also, this is a example of a static file, which is basically a report that was generated on the devices. So yeah, these are the different kinds of uh, uh, data that can be collected, and in our practice, we've been following this approach as well. So we have the clips themselves, and also some relevant static files with some uh, measurements or some annotations that was done during the standard of care practice, and also some relevant report information that was generated on the file on the machine itself. So yeah, so this is how the data is collected, and as I also said, this comes to a central location which is called a PACS. And yeah, also one thing you might see here is that so actually we cannot see the actual metadata of that I had mentioned previously here, because metadata open it through a PACS or but yeah, the data, as the data comes in, it's very important that we anonymize it. And also, there's a small detail here which I'd like to explain. So you might see that this top half of this image is cut off. So this was done because we might also have some critical patient information or personal information, sorry, that is embedded in the pixel data itself. So anonymizing the metadata does not clear that away. So in order to deal with that, what can be done, or what we did so far, is that crop the image at the top carefully. Patient is cut off, but the scan are not are left untouched, basically. So yeah, that's anonymization, and yeah, so the data comes in, it's anonymized and stored safely. So this is the data collection part, and yeah, as I also mentioned, besides these images, uh, for the study, like for example, depending upon the goal of the project or the goal of the study, we might also decide to collect some other relevant patient information, like as I said, the clinical history or the demographics and other stuff. So yeah, this is how a data collection pipeline could look like. And so yeah, after that, I'd like to talk about some challenges that might be faced, or speaking from our experience during this data collection process. So as I showed in this diagram, so basically these devices communicate with a central store or a central PACS through the internet. And it is quite essential that we have a pretty good internet connection to send these files over to the central server. Uh, because one reason being that ultrasound data can be quite huge. It's a whole different topic itself about compression of these DICOM files. So I'll just try to summarize that in a short way. So basically, like for example, if we have a study where we are collecting blind sweeps, for example, like 8 by 8 blind sweeps, let's say, for instance, and each of them are uncompressed. So each clip can go up to like 180 or 200 megabytes. And so let's say if each clip is 200 megabytes, and let's say uh, we have like 8 clips, so that can easily surpass like 1.5 gigabytes. So it can be pretty huge. So in order to transfer those files of those big sizes, we definitely need a pretty good internet connection, and that is actually one of the challenges that we have been facing in our data collection process. Uh, in our experience, due to these huge sizes of these DICOM files. And yeah, another challenge is like let's say, as mentioned in my previous slide, I said that along with these scans, like we might also decide, or we might need to collect some additional patient. They also need to be collected in a separate healthcare person, and other clinicians might need to alter their workflow as well, which can be a challenge in itself too. Because yes, as we all know that the main goal of clinicians is to serve the patients, and they might not always have adequate time to fill these questionnaires and uh, send them to the central server without any hindrance, for example. So yeah, that is another challenge. So the challenge is, I would say, is to make the process easy and seamless, so that the existing workflow of the clinicians is has to be altered as minimal as possible. So yeah, that's definitely a major challenge that we've been facing too. And definitely, yeah, so human errors during data collection is another challenge. Uh, like as I mentioned, these files can be pretty huge, and we need a proper internet connection to send them over to the central server. So there can be instances like the same study is sent multiple times, and if, like, for example, we are collecting patient information as well, so we need to link those studies with the patient information as well. So there might be some errors in that process as well. So yeah, this is a basic summary of the challenges that uh, that we've been facing, and obviously uh, someone else could face while collecting this kind of clinical ultrasound data. So yeah, so these are the challenges uh, uh, that could be faced. And so moving on. So once we have the data properly in this central packs, so the next step is to get them ready for the annotation process. Like, as I mentioned, anonymization is the first thing that we need to make sure of. And so after, anonymized data has been collected, then we need to assign these studies to the annotators for the annotation and labeling process. In our experience, what we've learned is that before starting the actual or the goal of the annotation, so that once the annotation process is started and annotators have started annotating the studies, we don't change the task in the middle. Uh, Otherwise, the effort that already has been put in might go to waste, or we might need to change the overall process in the middle as well. So yeah, it is very critical that the task is well defined at the beginning before starting the actual annotation process. So yeah, this is uh, closely linked to actually the type of model, or the type of, or yeah, basically the type of AI model that we are aiming to create. So based on that, the annotation process or the annotation questions, let's say, will be prepared. So it's very critical that we are pretty clear, and the annotation task is well defined before starting the actual annotations. So yeah, once the data is ready, it is anonymized, and the task is well defined, and we are clear on what we want the annotators to do. So the studies are next to be assigned to the annotators for annotations. So studies can be assigned in various ways to the annotators. So the most common ones, I would say, is random assignment. So basically what this means is we can randomly assign studies to the pool of annotators that we have. So let's say that we have 100 studies and, let's say, 5 annotators. So we can randomly sample data from our pool and equally assign them to the 5 annotators. So yeah, that's one approach. So another one is round robin, which is similar, but the approach that we can take here is basically once the studies come in and they are anonymized and ready to be assigned. So basically, we go in a round robin fashion and basically assign the studies one by one to the pool of annotators that we have. So we go. So basically, we can say that there is a queue of annotators waiting for studies to be assigned to them, and once the studies come in, we basically go in a round robin fashion and distribute studies to the annotators one by one. So there are different approaches, different ways to do this. So yeah, there's basically no one size fits all approach, I should say. So it basically depends on how we want to uh, plan and execute the annotation process. So yeah, this is briefly how the annotation process would work. So yeah, another thing, another important aspect of the annotation process is something called the inter-annotator agreement. So this is basically a practice by using which we try to figure out like how consistently different annotators are labeling or classifying the same data. So the goal is to evaluate the reliability of the annotation process, basically. So the main thing here is, the main thing that we are trying to figure out here is that, so if multiple people or multiple annotators independently give similar labels to the same data, we can be sure that the labeling task is well defined and clear, and the annotations that were done by the annotators are reliable and not overly subjective. So yeah, basically, if multiple people or multiple annotators agree or give the same labels to the same data, or give the same annotations to the same data, then basically, yeah, we can be sure that the task is well defined, and uh, we can also be sure that the annotations would be reliable and yeah, not overly subjective, as I said. So a simple example could be like, let's say we have three annotators, and we say, let's say that we tell them to label 10 ultrasound scans as either normal or abnormal. So, for instance, if all of them give the same labels for most of the scans, we can say that the agreement among themselves is high. Uh, and in the other case, in the negative case, like let's say if they disagree often and the agreement is low, so this might mean that there might be some the task, or there is some inconsistent criteria, which might mean that we might need to take one step back uh, and yeah, figure out what's going wrong, or let's say we need to let's say our task should be rethought or reworked, so that the ambiguity can be reduced and the inter-annotator agreement can be high. So yeah, this is a simple check that can be done before starting the actual annotation process to make sure that all the annotators are in sync, and it also could give us a idea about the annotation design itself. Like, is the criteria well defined, and is our goal well defined? So yeah, this is something that can be done before starting the actual annotation process. So once the data is ready, we have the data, and before starting the actual annotations, we can do this sort of test, so that in order to be sure of the in order to be sure that yeah, as I said, everyone is in sync and we can go ahead with the process. Yeah, so this is the inter-annotator agreement, and so yeah. So after that, I'd like to show some examples of the annotations that we've been doing. So in this slide, you can see a simple screenshot from our application that we've developed for our project for allowing annotators to annotate nine sweep blind nine nine blind sweep clips here. So this is so on the left you can see the various clips here, and we've named them sweep 1, sweep 2, sweep 3, sweep 4, and so on. These sweeps can be named depending on the type of study you are conducting. And so what clip annotations mean is that each clip is annotated separately on a set of defined questions. Like for example here, this first sweep has already been annotated, and this is what the annotators uh, annotated basically. So as you can see, for each clip, the annotator has to answer these set of questions like, is it a single versus multiple pregnancy? Is it ectopic or non-ectopic? The absolute placental location, the relative location of placenta, and going down, relative location of placenta to the cervix, placenta previa or non-previa, the fetal presentation, the cervix anatomy, presence of heartbeat, and the AFI index, and the trimester. So this is a simple example of an annotation. So basically, each annotator goes through of these clips that we have here. And also, please note that the annotator is not able to see any personal patient information here, because as I mentioned previously, the data is anonymized, and here also, since some of these devices might embed the patient information in the image itself. In order to deal with that, we had to crop the image here. So as you can see here, the patient information is not visible at all. Another thing is that the annotators are able to play this clip as well, so they can basically scroll here and go through all of these frames. So as mentioned previously, this clip is a multi-frame DICOM file. So this is basically a clip, so the annotators can play through it, go through it, and give the answers to these questions. So this is a clip level annotation and a simple example of what kind of questions can be put in the annotation form here. So yeah, this is the clip level annotation. And another type of annotation that we've been working with is the patient level or the study level annotation. So the idea here is that for clip level, its own set of questions and answers. What it means is that the annotator goes through all of these clips. So basically, these are 8 blind sweeps that were taken on site. So basically, the annotator goes through all of these clips and as a whole tries to answer these questions. This was the goal of our study here. This is the study level annotation. And also for the clip level annotations, we can have like different tools as well to measure various things here. Like for example, in this example, this is a clip level annotation where the annotator has to determine the AFI index and also the AFI landmark. So we've named it AFI landmark here, but this is actually the deepest vertical pocket. So basically, the annotator tries to scroll through the ultrasound scan and figure out in which of the frame is the deepest vertical pocket visible, and the annotator draws this line here. And yeah, so this is also done for each of the clips. So yeah, this was a different study than this one that we have here. So this is while this uh, annotation process was done by one of our researchers, one of our clinicians to build the AI model to predict or to find out the deepest vertical pocket from these scans. So this was done for that purpose. So yeah, so this is how an annotation system can look like. Uh, but yeah, this is the tool that we developed. But I'd like to say that there are various other tools as well, open source tools as well, that allow annotators to do this. Or if let's say you don't want to use a tool and uh, you want to basically do some annotations without building any tool or without using any of those softwares available. So basically, these scans are files. So basically, they can be downloaded or viewed using any like standard DICOM viewer, and separately any sort of form builder or some sort of tool that you decide to use. So yeah, so this is an example of what we've been doing with our annotations. So yeah, so going through the process. So as I said, the annotators do this. They annotate each of the studies that were assigned to them, and after that comes the part where we want to extract this data from the system for model training. So I want to show a simple example here is, or an example of what how it can be done. So each study can be grouped in this way. Like let's say we have, like as I said, in our study we had nine blind sweep protocols. So we had 9 sweeps. So we have the clips here exported from the system. And also, yeah, we have the static files as well that were collected during this study. So this is basically one study. So one study's clips and its static files. And also here as JSON. So basically this file will contain using this form. What this JSON file can look like is something like this. So they can be organized accordingly based on clips or for the study as a whole. So in our use case, we had to have all the annotations for the clips. So we have the names of the sweeps, and in JSON format, we have what was entered by the annotators for each of those sweeps. So this is for the AFI landmark study, this example that we have in this slide. So as you can see here, we did not have the study level or patient level annotations here. So that's why this patient annotation is empty here. So we only have the clip annotations for each of the clips. So yeah, this is just an example. So we decided to go this way in order to build the data set in this way and provide this annotations to our researchers so they can go ahead with the model training. So this was agreed with them. But yeah, this is not the status quo actually. So there might be different formats that the researchers would want. Like, for example, some researchers would prefer not JSON files or maybe XML files or even CSV files and so on and so forth. So yeah, this is just an example of what we did. And yeah, so this is here I want to show another example of the what the annotations would look like in the data set. So this is for actually this particular study that I showed here, where we have the annotators annotate all the clips separately and the whole study or the whole patient as a whole. So as we can see here, we have the patient annotations, which is for the overall study. And we can see here the questions that were the question and the answer that was given by the annotators. So these act like the labels for the data. So this is the patient annotations, and here we have the clip annotations grouped according to sweeps. So if we have 9 sweeps. So for each sweep, we have the this is how the data would look like. After that, yeah, this data is handed over to the researchers so that, as I said, they can move ahead with the model training process. So yeah, I think I covered the whole process from data collection to annotation design to how the annotations can be done, to how at the end the data can be exported and organized to be handed over to the clinician, to the researchers for their model training. So this is how the overall process can look like. At least we've been following this approach. So yeah, lastly, I would like to share some tools that can be used in order to build this pipeline, or in order to build this kind of tool, let's say, to facilitate data collection and the annotation process. So yeah, in order to collect DICOM data, obviously we would need a PACS. So Orthanc is a very commonly used open source PACS and a very popular one. Besides Orthanc, there are other PACS systems as well, which are available freely on the internet. So what we would need to do is we would need some technical expertise to set this up in a server somewhere and make our ultrasound devices communicate with the server so that the studies can be sent over to the PACS. So regarding anonymization, most of these PACS support anonymization out of the box. So these systems can be set up, like for example, when the data comes in, uh, before storing them, storing the data on the server, the anonymization process is done so that all the critical patient personal data is anonymized. So yeah, Orthanc is a open source PACS that can be used to collect and store the DICOM data from various sources. And regarding DICOM viewers, so actually in this slide that I just showed, so this is a DICOM web-based DICOM viewer, which allows us to visualize the scans staying in the browser itself. So obviously, in order to allow the annotators to uh, view and scroll through the scans, we need a DICOM viewer. So OIF is also one of the most popular tools, open source DICOM viewers that are available. So yeah, this viewer can be connected to a PACS backend. So basically, OIF can be connected to Orthanc. So data comes into Orthanc and it can be viewed through OIF, staying on the browser. So this is in the case we want to, like, let's say, allow our annotators to view the data on their browsers. So besides that, let's say if we don't want to use a web-based solution, we can also opt for some desktop solutions as well. So there's this useful tool also called VSys, which is an open source desktop DICOM viewer, which can be downloaded, and yeah, it can also open local data. Like, let's say we can allow the annotators to, let's say, download the data in their systems itself, and let them view the scans through this desktop viewer, for instance. Or these desktop DICOM viewers also uh, allow users to connect to a PAC system and grab the data from there. So yeah, this is also a useful tool, VSys, which can be used. And yeah, so as I said, to programmatically open the DICOM files and to manipulate them, or let's say we want to browse the tags that are browse the metadata that is in the DICOM files. So there's this wonderful library called PyDICOM in Python, in the Python programming language, that can be used to work with these DICOM files. And yeah, obviously, if like, let's say, for instance, we want to build a end-to-end system itself, like, for instance, this kind of system, we would need some back-end and front-end web development expertise so that uh, we can build this kind of system where users can log in and they can annotate the data, and and they can also be, the data at the end also can be exported from here. But yeah, as I said, to do the annotations, or to allow a group of annotators to annotate the data, it's not compulsory that we have this kind of system in place. We can always utilize these open source solutions to collect the data and view them through the browser or view them locally in the desktop. And yeah, also, as I said, we can design the annotation form in any form builder tool that we want. So it can be, for instance, simple as a template in a Microsoft Word file, or even, let's say, Google Forms. So yeah, these are some technical tools that can be used. So yeah, I think with that, that's all that I have to share. I had to share. So yeah, thank you for listening. And yeah, if there are any questions for me, I think I can take them. Thank you.
Okay. I'm hoping everybody has understood the entire session. We do have some claps. I think you can see those. I'd like to ask what questions you have. Perhaps either raise your hand or type in the chat so that we can hear some of the questions there is an activity that I'll be discussing that you'll be doing around pre-processing. But in the meantime, maybe I'd like to hear any questions or anybody who has a comment for Sukrit. I believe he'll be able to see the messages. Any questions? I think you can see the comments. Somebody did say it was a good presentation. Frank, you may unmute and just ask your question. Okay, Frank, we can't hear you. I see you're unmuted, but we can't hear you. Let's try again, Frank.
Hello, Victoria. Are you able to hear me now?
Yes, now we can hear you. Just go on.
Thank you so much. So I actually got something I didn't expect. So I initially thought that when we are annotating, we have to put those labels in the images, like maybe you put a mark on the image or the clip, and then you'll be able to insert that particular word or whatever you're doing within the image itself. But I've seen we actually have the annotations that can be put different from the images themselves. So how do we use that in training? Say how well will the model be able to identify the features if you wanted to identify features in the image, yet we have annotated them without putting marks linking them to the features of the image that we are looking at?
Chris, I hope you caught that.
Yeah. So I'll try to answer that question. Yeah, thank you for the question, Frank. So I think you were referring to one of the slides that I showed here, right? Let me share the screen again. Okay, so are you referring to this slide where the annotator just draws this line and we have no label assigned here?
Yes.
Yeah. So yeah, actually, this was a different use case. So we modeled it a bit differently here. So actually, as I said, this line here that we are seeing here is the AFI landmark. So basically, we allowed the user to add a measurement here, which would correspond to this AFI landmark. So basically, the label is the AFI landmark itself here, or to be more precise, this can be called the deepest vertical deepest vertical pocket. So we allowed the user to basically kind of let me put it this way. So we kind of simplified the process where the user just draws this portion where the user sees the deepest vertical pocket, and so that portion is labeled as the deepest vertical pocket or the AFI landmark here. So this is the label itself actually, but yeah, as you also said, so our tool that we used here, we in our tool that we used here, we followed this approach. But definitely, like for example, if we were to draw a bounding box, or let's say a simple segmentation here, we would definitely need to assign it a label as well. So Yeah. So yeah, this is pretty much the same thing. So in summary, this is pretty much the same thing. The label is this part itself, but we just like took this different approach here to make the life of the annotator a bit simple. So the annotator did not have to mention that this is the landmark that he or she is annotating. So basically, while answering this question, the annotator just draws the line, and this line corresponds to the landmark. So yeah, was I able to answer your question?
Yes, I've understood now.
Yeah, thank you.
All right. Any other person with a question?